It's a it's a real pleasure to have Subir Sachdev give us the Professor Subir Sachdev from Harvard give us the JQI seminar for this week. So Subir doesn't really need an introduction, so but but he made it really easy with his well-organized internet profile. So Subir got his PhD from Harvard in 1985 after a brief postdoc of 2 years at Bell. He became an assistant professor in 1987. He was there till 2005, where he did many things that we read about, including his wonderful book on quantum phase transitions. And in 2005, he moved to I think it's 2005 according to this, moved to Harvard University, and has been there since in the physics department. I didn't even realize that he was chair for 2 years in between this, at least from his research profile, I couldn't tell. Yeah, that's what I thought. This is an insanity. He's got several awards. Out of which I'll just mention the Onsager Prize. Particularly, it has a very compact citation for his seminal contributions to the theory of quantum phase transitions, quantum magnetisms, and fractionalized spin liquids, which is one of the things you'll talk about. All right, Subir, so I won't hold back.
Okay, so mic working?
It sounds good to us.
My mic, okay. My mask. All right, thank you, Jay. It's always a pleasure to be back at Maryland. I'm here frequently. I think I was here at JQI a few years ago, and I told Charles, you surely want me back. I was just there. But the campus is completely different every time I come. It's really amazing to see all the changes. And also, of course, I have a lot of friends here who I'm always happy to meet. All right, so I'm going to talk about really two related topics. When I was planning this talk, I thought, well, I should really talk about the work on Rydberg atoms and its connection to spin liquids, which is very current. But fortunately, I decided to add on something else because you're going to hear much more about Rydberg atoms and really the real story from Julia Semighini tomorrow. So I'll just introduce the topic, and all the difficult questions can go to her because she's the one who did the pioneering work there. All right, so let's see if it works. Okay, so here's the outline of my talk. I'll begin with just a general introduction to spin liquids and Z2 gauge theory. As you'll see, a somewhat biased introduction, but anyways, this is the way I'd like to think about it. And then I will talk about some exciting recent experiments which have pretty good evidence for a non-trivial spin liquid ground state. And then I'll turn to the Hubbard model, which motivated a lot of original studies on the spin liquids, especially in the cuprates, but also more recently, there are experiments on ultra cold atoms. And there's major puzzles there that have been longstanding, and I'll talk about our recent ideas to resolve those puzzles. So let me begin with a gentle introduction to spin liquid theory. So one place where spin liquids were first hypothesized to appear was in the triangular lattice antiferromagnet. So imagine you have some insulator where the electrons are localized on the sides of a triangular lattice. They can't move, but they have a free spin and a half, which can couple to its neighbors. And the spin coupling between nearest neighbors is antiferromagnetic. So this constant J is positive. So now if you minimize it classically, you get this state with the spins pointing with 1 to 20 degree angles to each other. But in the mid 1970s, Anderson hypothesized that perhaps there's another type of state, which doesn't, like this state, break spin rotation symmetry. There was a lot of emphasis on symmetry in the early days, but today, of course, we understand things much better. The symmetry is really beside the point. It's really that you get a new state which has some non-trivial, we use the word topological order, but I sometimes hesitate to use it. because now people talk about topological insulators and topological superconductors, which don't have topological order in the sense that I'm going to use it. But anyway, but for a while, that's what it was called. Anyway, and also, instead of thinking of spins, you could equally well think of hardcore bosons. Suppose you had a model, say in some ultra cold atomic system, where the boson number on any site is either 0 or 1. So again, there's two states on each site, the empty state or the occupied state. And these would correspond in the spin language to, say, the up state and the down state. And then you can immediately make this operator correspondence, where the boson is a spin flip operator. Note that this boson carries Sz equals 1. It has integer spin. And it's not fractionalized or anything. It's just another representation of the spin operator. And then the antiferromagnetic state would correspond to, if it corresponds to long range order in the S plus S minus. Okay, this pointer stopped working. Probably needs to be charged. I'll try my pointer, which I did charge in the morning. The antiferromagnetic state would correspond to some kind of superfluid state of the bosons. Okay. All right. Okay, now. Anyway, okay, I'll continue with this, don't worry. So here's an example of the kind of novel state that Anderson hypothesized. So you imagine that in this spin coupling, antiferromagnetic spin coupling, that the spins form in singlets. Get a singlet pair like this. In terms of the boson, this corresponds to a boson, a single boson, rattling back and forth between those two sites in a bonding orbital. All right, so one trial wave function you might write down is this configuration of singlet bonds, which, however, the actual ground state is not any particular configuration of single bonds, but it's a coherent superposition of all of them with these numbers that are so far undetermined. So this is the famous resonating valence ground state, where you just take a superposition of all possible configurations of these bonds. So it's the same idea as in benzene, where you have superposition of two configurations of the pi bonds, which goes back to the 1800s, before quantum mechanics was invented. And benzene, the structure of benzene is figured out by chemists. But here we're talking about a superposition of an infinite number of configurations. So the modern statement is this is a state, it's really the first wave function that anybody wrote down that had what we call long-range entanglement. It's really genuinely different from other states of solid state physics. The other famous state, the early state that has long-range entanglement is Laughlin's wave function of the fractional quantum Hall state. Okay, it depends how you define entanglement. I haven't defined entanglement, but okay.
I just wanted to see what you're thinking.
Yeah, I mean, people come up with very different definitions, and then there's always some exception that spoils the game, so I didn't define it precisely. But it's one of those things, you know what I mean.
Can I ask a quick question?
Yes.
Magnetic situation right now, maybe we'll talk about it.
Not for the so the triangle lattice itself with nearest neighbor coupling has long range order. It looks like this.
That's what I
Yeah, I don't think there's any question about that. But now you can take add more couplings, like a second neighbor coupling, a third neighbor coupling, or even something exchanges. Then there's a very complicated phase diagram, which has many different phases, including the phase I'll talk about, including the RVB phase, and also the analog of Laughlin's phase, which in this case would be called the chiral spin liquid. And they've both been seen and they're stable and so on. In theory, in numerical work.
But in numerics also.
I'm talking about numerics. The theory, well, okay, I'll tell you the theory where I think the stability of the two types of states, the chiral spin liquid and the RVB state, was established very early on. And that's in fact just my next slide. So the theory of this resonating valence bond state as written is what we call the Z2 spin liquid. And the main thing we realized is that you should really think about this state as a deconfined state of a Z2 gauge theory. So there's an Ising gauge theory, which had been studied earlier by Wegner as a model of quark confinement, where it had two phases, a confining phase, where the matter fields were like quarks were confined, and the other one where they were free. And now this is so it's very much like QCD or quantum electrodynamics, but the gauge symmetry is much smaller. In QCD, you have the rotation of 3x3 matrices. In electromagnetism, you have a U1 phase factor, and the charges can be any integer you want. In Z2, you just have plus or minus 1 as your gauge degrees of freedom. And any object either carries a gauge charge, which is 1 or minus 1, it doesn't matter, or it has no charge, which is 0. So the question is, is there a phase in which the quarks are free? That is, they're not confined as in quantum chromodynamics, but you have a phase of Z2 gauge theory where the quarks are free. And Wegener had shown in 1976 already that in a Z2 gauge theory, there are free quarks. And what we showed, we made the connection that in fact the RBB state is precisely that state. And had many other properties which we described, in particular in 2 dimension, in addition to having these quarks that carry Z2 electric charges, which we now call spin-ons, as I'll show you what they are. There are also objects that carry magnetic flux. So this Wegener didn't talk about. And these, in one community, are called visons. In another community of people who work from the toric code are called the M particle, and the spin-ons are the E particle if they're bosons. And there's also a bound state of the 2 of them, the epsilon particle, which is called a fermion. Now, in the case you have a system where the boson number is conserved, then another property of these Z2 gauge charges is that you can get fractional quantum numbers. You can have excitations in terms of boson, which have boson number 1/2, okay, like the spin-ons. So these are the topological excitations because you cannot create them by any local operator. Anything you do locally will always create a pair of them. And of course, then Kitaev pointed out that if you took these objects, topological objects, which are insensitive, cannot be created by local operators, that if you braid them, you can do topologically protected quantum computing, not with this one, but in more complicated, more complicated spin liquid states. And these phase factors that you pick up as they move around each other are insensitive to essentially all local noise. So let me show you in this example how you get these anyons, which characterize this very simple state of Anderson. So for example, here's a state, and you hit it with this. If you think in terms of bosons, so you have one boson rattling back and forth on these 2 points. So we can add another boson. Oops, where I have 2 of these, and that's the up state in terms of the spins. So I have these 2 up states. But now you could imagine a fractionalized situation where these 2 states move apart, and that's the spin-on. Now you only added 1 boson, but you have 2 excitations. By symmetry, each excitation carries boson number 1/2. So you've got now spin 1/2, boson number 1/2 or spin 1/2 excitations, which are anyons, because you cannot create any one of them by a local operator. You can only create a pair. But this could, one of them could run up to infinity. So you could have your little quantum computer with only one of them. If you're so lucky, then you have a protected object that you can do things with. Okay, so that's the E particle or the spin-on. But there's another particle that you can create, which I'm going to call the vison, and it's like a Z2 magnetic flux. But let me show you just in very simple term what this vison is. So remember, I had a ground state wave function with the superposition of all possible dimer configurations with some coefficient CD. And now all I do is I introduce this phase factor of plus or minus 1, which simply counts the number of bonds crossing this red line. So you take a branch cut anywhere you want, starting from the red circle. And now in this configuration, there's 1 bond crossing it. So you pick up a -1. But as the dimers resonate, this is still -1, that's still -1. But if you resonate around the center, then you can change the number. And now this is +1, and so on. So yeah, there's infinite number of terms. You're just going to change a few of them a little bit. And that will give you an excitation which actually just sits here. This branch cut is totally invisible to you. And that's sort of like a gauge symmetry of the problem, because you're only able to measure things that go around in closed loops. And if you go around in a closed loop, you're always going to, any loop that that crosses this branch cut will cross it an even number of times, and so you won't pick up any phase factor. Anyway, so that's kind of why it becomes a Z2 gauge theory. You can think of these dimer present or not as a Z2 gauge field, much like the electromagnetic gauge field. It's like the Aharonov-Bohm phase factor as a spin-on moves from one side to the other. And right here is like a vortex. It's a vortex can have only two values of the flux, -1 or 1. And so this just costs a finite amount of energy. So there's just another object that must be there in this Z2 gauge theory. Yes.
And so going back to the spin-ons,
Yeah.
I mean, I haven't thought of these in terms of bosons before. So if I think of it as bosons, so I would think that but it sounds like if I go up and if it's up and down, that's like a boson is localized on one of the sides and not on the other. So
No. You should think of, well, you should think of this is what this ellipse represents.
Yeah.
It represents a boson.
Yeah.
It's not localized. It's on the bond. You should really think of it sitting on the bond.
No, not that configuration. Once I have the spin-ons that are far apart. So like yeah, for example here.
Yeah, well, okay, it's going to be moving around in a way that you're not here.
But is there a sense in which there's half charge or half boson number precisely? Is that, or is it just more like
As long as they're well separated, if you integrate the boson number around any one of them, you're going to get 1/2. But it's having a lot of 0-point motion. It's not sitting in one place. Yeah, the total charge here, I mean, of course, there's a background charge of half a boson per site. And then if you, it's not so different from Majorana's. Yeah. Well, okay, so now I hesitate to use the domain walls when you do it in one dimension. Then you have actually a broken symmetry, and those not strictly speaking anyons. So this kind of physics cannot happen in one dimension. At least the analog of this phase doesn't exist in one dimension. Yeah. Yeah, it's similar to that, but this is, it's a more subtle thing. And I think it was Kivelson who first pointed out, because he had been working on the polyacetylene when RVV came out. And then he pointed out, well, these objects which were just domain walls now become fractionally charged in a spin liquid. Okay. All right, so you have these flux excitations, which can now the center of that can also move around. And now if you imagine taking a spin-on or this extra half boson around one of these visons or the M particle, you have to cross the branch cut once. And when you cross the branch cut, you'll pick up a phase factor of -1. It's only when you cross it once that you pick up a -1. If you cross it twice, you don't get anything. So these objects are relative semions, as it's called, because you pick up a -1. One very important difference from something like the fractional quantum Hall effect, these are not chiral. It doesn't matter whether you go this way or that way, you get the same phase factor. And so this is not a chiral theory. You don't need strong magnetic fields or anything to break time reversal symmetry. It's completely compatible with time reversal symmetry. And of course, in the early days, there were a lot of arguments, because there was certainly a period when many people, including Laughlin, believed that the only way you could get anyons was by the Laughlin state, naturally. So this was really the first counterexample, and that's not true. But since then, we also understand that there's a Chern-Simons description of these states. It's possible to write down Chern-Simons theories which preserve time reversal. These are so-called double Chern-Simons theory, and well, you have one of the world's experts, Mason, who can tell you much more about all of these states. Okay, and all right, fine. All right, so now let's talk about Rydberg atoms as a Z2 gauge theory. So one of the neat things is you can write down the Rydberg Hamiltonian on certain lattices exactly as a Z2 gauge theory with some matter fields. The matter fields in this case would be spin-ons. That's what I mean by matter fields. And you notice here in the ground state, this ground state here, there are no spin-ons. So you want to really, the matter fields are not good. If you have a lot of matter fields in the ground state, they will condense and you get magnetic order. If they're bosons, or they'll do something else. So you want to suppress free gauge charges to get a deconfined phase. And that's really the name of the game in the Rydberg Hamiltonian. How do you suppress the free gauge charges so that you have a liquid phase which has long range entanglement? Okay, so this is the theory work here is with many people. Some of them who used to be at Harvard. Currently, Ryan is about to go to Princeton as a postdoc, and Darshan is a postdoc at Harvard. Yanting is one of my current students, and Wenwei is now at Stanford, and Hannes is in Austria, in Innsbruck, and of course you all know Misha. And the experimental side, I think you'll hear much more from Julia tomorrow on the various people involved. Okay, so this is a cartoon picture of a Rydberg atom. So you have a Rydberg atom which is trapped by these tweezers. And as a theorist, all I think of this Rydberg atom is a two-state system. It's a two-level system. There's the ground state and there's the excited state. So there's a two-level system, and you can undergo transitions between this state and that state with the Rabi frequencies omega. So there's another laser which is almost in resonance between, well, actually it's just two of them, between this ground state and the excited state, this ground state and the excited state. And in the rotating reference frame, you can just think of them as having a very small energy level difference omega. Okay, and this delta then is the splitting, not the splitting, it's the off detuning, as it's called, between the laser frequency and the actual energy splitting between these two states. Okay, so this is just a two-level system. You're going to spin in a Z field and an X field. And what's very nice about the system is that the offside coupling is very strong. So it immediately gives you, overcomes a major problem in many cold atom situations where the interactions are just very local. Here they're highly non-local because when you have two Rydberg atoms, they repel each other greatly by a van der Waals interaction that falls off as 1/r⁶. And it's repulsive because these are excited state, not ground states. So basically, you have what's called the Rydberg blockade. If you have two nearby atoms, then this interaction is so large that it's rare that both of them would be excited. It costs you much more energy. So having, another way to say it, having a Rydberg atom nearby, if you now try to excite this state to this atom to its excited state, it's going to be totally off resonant. It's not going to go there because of this extra energy you have to pay because of the van der Waals repulsion. All right, so there were many experiments in 1D, which I won't talk about. So here's the Hamiltonian written in a boson language, where the ground state is the empty state and the excited state is the boson. I should really make this a capital B to correspond to the previous bosons I was talking about. So you have however, here the boson number is not conserved, unlike the pictures I was showing you. You can freely add or remove a boson from the vacuum. That's the Rabi term that's flipping you back and forth between, so this is the picture of the two lasers. There's your ground state and there's your Rydberg state. Okay, and delta is this very tiny detuning over there. Okay, so there's two states. These are hardcore bosons, 0 and 1. And a long time ago, before we knew anything about such systems, we had studied this for completely different reasons, having to do with tilted lattice experiments that was done by Michael Schreiner and many others, where these bosons had a different interpretation. Anyway, fortunately, we had studied it and worked out some phase diagrams, which were then examined in various 1D experiments using Rydberg model. Okay. So let me just jump ahead then to the Rydberg experiments, which were done on two types of lattices, which you'll hear much more about. I think you'll more hear about the second type. This is on the, imagine you put the Rydberg atoms now on the Kagome lattice. So I just take this model where I can create or annihilate bosons on any of the blue sites. And there's my Hamiltonian. So the first thing I will do is to rewrite this as a spin model. So B plus B dagger will become sigma Z, and L will become 1 minus sigma X. So sigma X equals -1 corresponds to a Rydberg state. Sigma X equals 0 corresponds, +1 corresponds to an empty state or a ground state of the atom. Okay, and what will happen is that the sigma Z operator will become the Z2 gauge field. The thing that this term right here with some, which creates and removes a boson is what plays the role of the Z2 gauge field. Okay, so I'll show you that in a minute. So now just rewritten the same Hamiltonian with no changes. This doesn't look like a gauge theory at this point. This is completely exact. But now I'm going to do the following. I'm not making any changes. This is just a mathematical trick, which allows you to see some of the physics more clearly. So what I'm going to take is take every sigma Z term and write it as tau Z, sigma Z, tau Z. And the tau Z's sit on the red sites, which are the centers of the hexagon of the Kagome lattice. And so that's where the tau Z are. And these will be the matter fields, the spin-ons. Okay, so first just look at this. I just replaced this by this. That's all I did. But really, you can quickly see that this doesn't do anything because there's a gauge invariance in the problem. If I do a gauge transformation, this is very much like electromagnetic gauge transformation, where the gauge transformation is rho I, which is plus or minus 1. It can be different on different sites. If I gauge transform tau Z this way and sigma Z this way, so remember it has a, so sigma Z is sitting on the bonds, if you wish, of the triangle lattice right here. Now I think of each site as sitting on the between two red sites. So when I do a gauge transformation, I flip, the rho I act on the red side, the triangle lattice, and I flip this thing. So just by doing a gauge transformation, picking a gauge, I can go back to the original model. So I haven't done anything. I've just made it a lot of redundant. But now the key thing is I want to work in this gauge language. So I put this constraint. The constraint says the product of tau X and on any site of the triangle lattice, I'm going to introduce this tau X operator, which is going to be the number operator of the spin-on. That is always chosen so that the product of all of these, so that if I look at the sigma Z here, sigma Z there, sigma Z there, sigma Z there, then that fixes the tau state on this point. So that tells me I haven't expanded the Hilbert space at all. Once I put this gauge constraint, which is like a Gauss's law constraint, like del dot E equals 0 or equals rho. In this case, the tau is this product of sigma X and all the bonds is like del dot E, and this thing is like rho. So that's why it's Gauss's law. And the Gauss's law in the Z2 gauge theory tells you that there are no extra states. This is just exactly the same Hilbert space, exactly the same objects, but it's nice to write it down this way because now it's explicitly a Z2 gauge theory with the Z2 gauge invariance. Okay, so there's a lot of fancy manipulation. Why am I doing all of this? Well, I want to imagine a configuration where I have a lot of resonance between the Rydberg atoms. So for example, what I'm going to do now, every time this sigma Z is excited, I have a Rydberg atom. So I'm going to represent the Rydberg atom by a bond. So each atom becomes a bond between the sides of the triangular lattice. And now, if I have some terms that are in the Hamiltonian that generate a resonance like this, then I'm going to get a spin liquid state. And the nice thing about this resonance and this gauge language is that it commutes with this constraint. If it's satisfied in this state, it'll also be satisfied in this state. So that's really the reason for writing it down. Okay, so this is a lot of fun and games. We could, you can do this on the Kagome and triangular lattices. But now it's a question, are the parameters right, so that this resonance happens a lot and you get a spin liquid. Okay, so that answer, I'll turn to that question. What is the next slide? The answer so far is we don't know for this lattice. We're still working on that question. But then our colleagues, Ruben Verison and Ashwin, around the same time or a bit later, proposed another lattice that would work better. And that's the where you put the blue sites, the Rydberg atoms on the blue sites. These are the vertices of what's called the Ruby lattice, which is the midpoints of a Kagame lattice. So now the Rydberg atoms are here, and now the resonance, for example, of 3 excited sites, is on the links of a Kagame lattice. So roughly speaking, the Rydberg model looks like a quantum dimer model on the triangular lattice when you put the Rydberg atoms in a Kagame lattice. I know it's confusing. And they look like a quantum dimer model in the Kagame lattice when you put the Rydberg atoms on the links of a Ruby lattice. And it turns out these are the only 2 lattices for which these connections work. We tried to for the square lattice or the triangular lattice. You put the Rydberg atoms on a square lattice, it just doesn't work as easily. Anyway, so this brilliant idea of Ruben and of Ashwin, in fact, does work. So they did some numerical studies on a semi-realistic model of this and got pretty good evidence for, well, in some models, very good evidence for a spin liquid phase with the spin on. And,
That's
right.
energetic. I was going to ask. So there is some energetics.
Absolutely, did some DMRG. We've also done a lot of DMRG on this, and okay, I'll show you some of the results. So here's Ryan's results in the DMRG, where you put the Rydberg atoms on a Kagame lattice. So you get, kind of trivial phases. You also get broken symmetry phases with different atomic arrangements, and which have also been seen in experiments. I think Julia will confirm, although that hasn't been published. But one of the things we saw was there was a very promising regime here where maybe there's a spin liquid. We've still been studying that for a year, some in collaboration with Ziyang Meng's group in Hong Kong. And anyway.
So what's the diagnostic you look at?
Everything you can think of. So I'm not claiming we have seen it.
Still, it cannot be quite absolutely certain. That's what you're saying.
Yeah, we're not certain there. We haven't seen the 4-fold Legendre torus, for example. But for this lattice here, these are not our result. Ruben, for a certain model, is definitely been seen. Whether it's in the experiment, I think, okay, I'll show you the experimental data. There's still a few issues in the experiments, but the signs are very encouraging. Okay. So this is the experiment which Julia G. Samaghini will talk about tomorrow, where we took the Rydberg atoms on the Kagame lattice. This is an actual picture of the atoms and which one of them are excited. So if okay, here you show all the atoms, I think. No, you only show the excited atoms. So every place you have an excited atom, you make this dimer. Okay. And now
so this is the lattice Ruben proposed, not Ryan's.
Correct, yes. The Ruby lattice. So, and now you, you just take a snapshot. You have and they're doing their thing, you take a snapshot. Every time you take a snapshot, you see a different configuration of excited states. And you look at all of those states. So this is one snapshot. And now the key thing is if you think of each excited state as a dimer, you can see this very close to a close packed configuration of dimers on the Kagame lattice. So that the statement then is that if there were only the dimer configuration, then you'll get exactly Anderson's wave function, just a superposition of different close packed dimer configurations of excited Rydberg atoms. There are, of course, defects. There are some spin-ons floating around, probably also visons, but you can't see them from this type of experiment. And really the question is, are the spin-ons and visons just virtual fluctuations that are there for a while, but don't appear to modify the long-range topological order, or they're really giving you some more trivial state? And that's really the difficult question, which needs to be answered. I don't think there's a definitive answer to that experimentally.
Maybe we discuss tomorrow, but unfortunately we missed the talk tomorrow because Team 5 Mac is giving a talk exactly at the same time.
Yes.
How large is this system? Maybe I should ask this experiment.
Yeah, Julia can answer that.
290.
Okay. All right, that's more precise than I would have known.
Oh, that's what I want.
All right, and I think Julia will also, so one of the things they can measure is precisely these Wilson loop operators. So here what you're doing is you're, if I can remember this right, you take a loop, and then for every loop, you measure the number of dimers around the loop, and you see whether it fluctuates from odd to even. And if it has a stable sign, then you're again confident that you're going to get a deconfined phase. Now, of course, this is a Z2 gateway with matter, and I'm sure some of you know, ultimately, there's no difference between area and perimeter loss at very large distances, but at least over reasonable distances that you're looking at, it can give you some sign whether you're really sampling correctly only the dimer configurations. And there's very encouraging evidence for that in this data here, which is measuring the Wilson loop, which is a product of sigma x. It detects close back dimers, but also more interestingly, there's this coherence operator, which is a product of sigma z in this case, which measures the coherence between, between all these states. So here's a state with one dimer, so here's a off diagonal term where you're resonating from this to this, or from this to this, and it measures whether that coherence is present, again, by looking at loops. And so this is more subtle, and another beautiful innovation by, I think, Ruben and Julia, which tells you that it's not just a superposition, here's the wave function. Now you could have a classical system, a liquid of dimers, which has all of these states, but then every time you looked at it and you saw this or that, they would appear with a random phase factor. This is telling you that the phase factors in front of these are stable. There's a coherence, and it's actually a superposition. It's sort of like a macroscopic cat state of many, many dimer configurations. All right. Okay, so you'll hear much more about this tomorrow. I'm doing on time. I can pause for questions anyway, or you can hold them till Julia tomorrow. Yes.
What's the in the ground state versus some excited state?
That's a perfect question for Julia. Go ahead, Julia.
Sorry, I have a question.
What is the in the ground state versus some excited state or finite density?
Yeah,
state?
so that's a very good question. So one of the subtleties that Subir mentioned in passing is that when they did the simulations, they first use the simplified model where you don't use the 1/6 interaction, but the PXP model where you have infinite interaction within a certain range and 0 alpha. And then you have a very stable symmetry in the ground state. If you start including the 1/6, these together will be more stable. And it looks like from the simulations which are finite and so on. So there could be some effects due to the finite size of the simulation, but it looks like the spin liquid gets unstable, and you just end up in a solid state, in a VDS, valid strong solid. But in the experiment, we see these sort of these signatures of topological correlation. So what it looks like is that we're not able to prepare this solid phase because it's a first order phase transition, but somehow we end up in this superposition of dimer configurations. So our interpretation is that it's a sort of metastable spin liquid with a finite density of defects. We have anions and things like that. But I think on that, there is a little bit more to investigate on what exactly is going on there. If the numerical estimations are correct, and if our interpretation of the that makes sense. So, yeah.
Okay. All right, so now let me change gears of another place where I think the ideas of spin liquids, which have been around, of course, for a long time, are, I think, becoming quite relevant for experiments. So this is work with my former postdoc, Yahui Zhang, who's now, who's now on the faculty at Johns Hopkins, nearby here. So please invite him down for a talk if you want to hear more. My current student, Alexander Nikolenko, who's from Ukraine, has a family in Ukraine these days, but still working hard on physics. Maria Tikhanovskaya, who's also my graduate student, and also Dirk Moore at the University of Chicago, and his student, Eric Mascott. Okay, so this is a cold atom experiment of ultra-cold fermionic atoms with spin a half on the square lattice by Emanuel Bloch's group. And that's meant to be, of course, a quantum simulation of the cuprate superconductors. And they see a phase diagram here as a function of, so delta equals 0 is the insulator, where you have one atom per site, where it forms an antiferromagnet. So that's been very clearly seen in the experiments. Then you add some doping delta, and there's apparently a Fermi liquid phase here. And okay, hopefully a superconductor, although that's not been seen in the cold atom experiments yet.
What the model you're simulating, Hubbard or?
Hubbard model. It's a Hubbard model, pure Hubbard. But now my interest right now is on the higher temperature behavior, which is accessible in the cold atom experiments, and also has been accessible for many years with more and more precise experiments in the cuprates. So here, it's clear that there's something very interesting going on. There's what they call the polaronic regime, which I will call the pseudo gap metal, and okay, fine. And there's a crossover, which it's called the strange metal regime in the cuprates, and then the Fermi liquid here. So my attention is really on this polaronic regime here, and I'm going to argue that this regime is best understood using spin liquid physics. That is not to say, maybe in some ways similar to what Julia was just saying, that a spin liquid survives all the way down to 0 temperature. There's a lot of indication in the experiments from the electronic experiment that it does not, that there's some kind of confinement crossover or even a phase transition to more conventional state. But nevertheless, I'll argue that really using spin liquid phase is the best way to understand what's going on up here. And that gives you control description. And then, of course, you have the challenging problem, what happens as you lower the temperature, which we are working on very hard. So one of the things they see when they cross over from here to here, so what they're able to do is a type of experiments you can't do in condensed matter. They see some vacancies moving around every time they look at a snapshot. And around the vacancies, they measure the spin correlations of all the atoms. So the other sites are not vacancies, there's an empty site. And so you have some density of vacancies, that's delta. And then you have these spin a half fermions moving all around. So really, the one big difference between this system and what we just talked about, the Rydberg atoms are really bosonic qubits. And these are fermionic qubits, because each site can either be empty or have a fermion which is spin up or down, and these fermions are moving. So it's in terms of quantum simulation or putting on a classical computer, it's a problem that's much, much harder. The other problem, you can make a lot of progress on a computer, regular computer. This one is almost impossible because of the fermionic nature. Okay, so you have this empty site, and then you measure the correlation. Every time you see a site, you measure all the spins around it, and you measure all kinds of correlations. And what they see with these color maps is that there's a dramatic change, even up here, between the kind of correlations you see here and what you see there. Okay, I'll just leave it at that. So there's the phase diagram in the cuprate superconductors of YBCO, where you again see dramatic change in observations as you go from the pseudo gap metal on the left. Where's the pointer? I don't know. It keeps disappearing on me. Yeah. Let me try this one.
So you're becoming less efficient than you used to be.
This is not my computer.
Oh, I was wondering.
Yeah. Okay, well, I don't know. I can't see any pointer. Sorry about that. Well, okay. I'll just have to use my words. Okay, so you go at the higher temperature regime. On the right, you have the Fermi liquid, and you have the pseudo gap metal. And I won't show you the data right now. I will show you the data when I first present the theory. But let me say, 20 plus years of experimentation in the pseudo gap metal have revealed a real mystery. Is there, first of all, it's a metal. Everyone agrees on that. Now, the basic metal that you get in solid state physics has a Fermi surface. And the Fermi surface in zeroth order has states inside is occupied and state outside is empty. But then there's also a very deep theorem called the Legendre Theorem, that the volume enclosed by the Fermi surface is a topological invariant. That is, you start with a free electron gas with a Fermi surface, and then you crank up the interactions to whatever you want. As long as the system remains a metal, the shape of the Fermi surface might change, but it'll change in a way that it preserves the volume enclosed. So in an experiment, if you see a Fermi surface, you can just measure the volume enclosed by it and see if it corresponds to the density of electrons. So that's the Legendre relation, and it's beautifully obeyed in thousands of experiments and all kinds of materials. And it's also obeyed in the cuprates in the FL regime on the right side. But on the left side, people are still debating what's going on, but it's clearly not a regular Fermi surface. I think everyone agrees on that. It's not a Fermi surface that obeys the Legendre relation. So people have all kinds of theories, but I would say the theory that's most reasonable, of course, that's my bias, is a Fermi surface. Is still a Fermi surface. It's still a metal, but it does not obey the Legendre relation.
So can you remind us, the Husband-Alpha effect seen on both sides, the full star and
okay, so
to know the volume, we have to have some experience.
Yeah. Yes. Okay. The Husband-Alpha on the right side is completely settled. No question, it works. On the left side, yes, they see what we call quantum oscillations, but those are at very low temperatures, where you also have charge density waves. Yeah. Okay. So then the question becomes more delicate. Once you break down spatial symmetry, then you have to look at the new unit cell of the charge density wave and ask, what is true that if you try to take a free electron gas moving in the charge density wave, you cannot understand the data. But that's not so that doesn't prove a valid Legendre theorem. It's a model.
But the simplest thing has been done and it doesn't work.
It doesn't work. So, but the other question is what's been done at higher temperatures? I don't know if I'm showing the data. They are not the Husband-Alpha. There's something called ADMR, which is angle-dependent magnetoresistance, and that can also be used to compute Fermi surface volume. And that's a paper published by Brad Ramshaw and Louis Taillefer in Nature Physics literally weeks ago, and that does see a violation of Legendre theorem. But the interpretation of ADMR is a little more subtle. It's not as clean cut as the Husband-Alpha. Yes. Right. Anyway, so what is this? So our proposal is what the state we call FL star, which is a metal which doesn't obey the Legendre relation. And the basic idea is that spin liquids allow you to do it. If you have a spin liquid, you can do all kinds of wonderful things. You can not only do quantum computing, you can violate the Legendre relation. And one simple way to see this is you take a condo lattice. Suppose I take a bunch of electrons that are not moving, which are literally spins, which we call the F electrons in some condo material. And then another bunch of electrons that are moving around and forming a movement. Now, if these bunch of electrons that are not moving form a spin liquid, say they're sitting on a nice triangle or a Kagame lattice, and they form a spin liquid, and then the other ones form a conduction band, then you get a state which we call FL star, which violates the Legendre theorem, because Legendre theorem would say that you should get a Fermi surface which counts the number of moving electrons and stationary electrons. But if the stationary electrons form a spin liquid, you have a violation of the Legendre theorem. So in the condo lattice, there are two states, one of which is seen in most of the experiments, where you see the large Fermi surface, which obeys the regular Legendre theorem. But there are also recent experiments which are showing indication of this FL star state. Okay, that's all very well. Everyone can understand why you might violate the Legendre theorem on a Kondo lattice, but we don't have a Kondo lattice. We have a Hubbard model with a single band. So roughly speaking, somehow I have to pick out some electrons, have them form a spin liquid, and have the others form a Fermi surface. How do we do that? Well, there's literally 1,000 papers trying to do that, including many by me. And I'm here to tell you, I now know a much simpler way to do it, thanks to Yahui's idea. And this is all you need to know. So I'll show you the way to do it correctly. All right, so this is the simplest way to take a single band model and somehow in a democratic way form a spin liquid of some of the electrons and have the others moving around. And actually write down a wave function for such a thing. And that's what I'll tell you about and end. Okay. I have about 5-10 minutes, is that right? Okay. All right, so you start with the Hubbard model. Now I got a pointer, great. You start with the Hubbard model of electrons, say on the square lattice. And then you do what's called the Hubbard-Trutanovich coupling. You write the Hubbard interaction as the square of the spin. And then you introduce a field phi, which is a vector, which when you integrate over the vector phi, which is the spin vector, you get back the original Hubbard model. So this kind of thing has been done starting from, I don't know, Burke and Schrieffer in the 1960s. It's called the Paramagnon Theory. It applied very successfully to the superfluidity in liquid helium, where the paramagnons were magnetic objects, which are nearly ferromagnetic. And this leads to P-wave superconductivity in helium-3. That's the basic theory, which has been well accepted for a long time. Then you can try to do the same thing on the square lattice for the Hubbard model. And this was actually done by Scalapino before the discovery of ITC. And he predicted this gives you paramagnon that are mostly anti-ferromagnetic, and they will give you D-wave superconductivity, both of which are correct. So that's quite a triumph for theory. But then we are interested in more than just that. We want to understand this. He didn't predict ITC, but anyway. But he predicted a lot of basic features of this paramagnon phi coupled to the electrons. So this is just an exact representation of the physics of the Hubbard model so far. Now what I'm going to do is imagine I integrate out some high energy electrons. I want to think of the paramagnon as a real degree of freedom, a quantum degree of freedom. I want to write on a Hamiltonian for it. So I give it some kinetic energy, this L squared. I just added the L squared term, where L is canonically conjugate to phi. Okay. And I also imagine there's some potential for phi, which is also there when you do some RG, and I replace the potential by a fixed length constraint. So what I have then is the paramagnon is a bunch of rotors. It's not a spin, it's a rotor, and that distinction is really important. It's like a particle which is moving on a sphere. So a particle moving on a sphere, the ground state would be the L equals 0 state. The first excited state would be the L equals 1 state. It's like a P-wave wave function. And the R operator, the position operator, if you hit the position operator on the ground state, you get the first excited state. So the position operator of the rotor or the particle moving on the sphere is the phi. The phi is the thing that takes you from a singlet to a triplet or back. Okay, so phi is a spin 1 object. In fact, the rotor has no definite spin. It can have spin 0, it can spin 1, it can spin 2, so on. So I'm going to, of course, the eigenstates here are these infinite set of angular momentum states that you know of this Hamiltonian. So I want to just truncate, take 0 and 1. So I have a singlet and a triplet. Well, what's the best way to get a singlet and a triplet? Is just a pair of spins. So I'm going to replace the paramagnon by these ancillary degrees of freedom. Now, I haven't added any degrees of freedom. As you'll see here, the idea here is by having ancillary qubits, which you can write down more complicated wave functions. on the physical Hilbert space. This is now a very common idea in all kinds of tensor network calculations. You take your physical qubits and then you introduce some other qubits and you write down some simple state of all of these, and then you project the whole thing down to the physical space. That's, I mean, the whole parton description is another formulation of that, really. Okay, so I'm going to answer these ancillar degrees of freedom with some interaction J-perp between them. And I'm going to couple them to the physical layer by this JK. So now, if J-perp is very large, then, well, let me forget that. These spins can form a singlet. And I'm back to my original model. So my claim is that if I do perturbation theory in JK with J-perp large, I will get back the Hubbard model. I'll get back the original Hubbard model. And it's now instead of having my electrons coupled with strong interaction on the layer, I've moved the interactions off to these ancillar qubits. And when I get rid of the ancillar qubit, I get back the Hubbard model. And you can really show this analytically in a perturbation theory in JK. So anyway, so if I want to get a large Fermi surface, as in the Fermi liquid, it's trivial now. I just project all the ancillars to singlets, so they're gone. And then I have my large Fermi surface. Okay, so far nothing new. I'm just doing a lot of formalism, telling you things you already know. Just thinking of the ancillars as a pair of the paramagnons as a spin. It's not a ladder. This is in 2 dimensions as a bilayer antiferromagnet. However, now I can write down another interesting state, which is right here. So imagine what happens is that the second ancillar layers forms a spin liquid. So these are just spins. These are bosonic qubits, just like in the Rydberg system. And maybe they form a spin liquid. Which spin liquid? I don't care. Any spin liquid. They form some spin liquid. And to 0th order, I can forget about them. They've just gapped out and formed a spin liquid. There's 1 qubit on every site, and they form your favorite spin liquid. But the first ancillar layer, these are spin I have sitting there. Now, if I look at the first 2, the physical layer and the first ancillar layer, that's a Kondo lattice. I have conduction electron moving around and 1 layer of spins. Now, I don't want this middle layer to form a spin liquid, then the first layer would form a large Fermi surface. What I want to do is have what's called the heavy Fermi liquid state. I want these spins to have a Kondo hybridization with the conduction electron and form a conventional large Lattice volume Fermi surface. So, okay, so if I ignore the second layer, then I do the obvious thing with the first 2 layers. I just have them obey Legendre theorem as if the second layer was not present. Okay, so in effect, I've added a density 1 from these electrons here. So what is the Lattice volume of these 2 layers? Well, this had density 1 plus p, as I told you there. So the total density is 2 plus p. Everything is modulo p, so that's p. Modulo 2, excuse me. So therefore, ignoring the second layer gives me the conventional Legendre argument, gives me the wrong size Fermi surface. But of course, the second layer is there, and it has excitations that are fractionalized and they're anyons. And so for the complete system, the original Hubbard model, I have exactly what I need. I have a Legendre volume that breaks, a small Fermi surface that breaks the Legendre relation. And some deep theorems tell me that can only happen if you had anyons. And indeed, I have the anyons, but they're at the bottom there. Okay, so they have to be there. And this just gives you a very nice way of getting this, and you can now write down a simple wave function. The hard part is this large part of projecting onto the singlet subspace of the 2 layers to avoid. It's hard to implement numerically, but people are working on it. Anyway, I think I'm out of time. So starting from this point, we can do a lot of computations. We can compute the Fermi surface in this FL star state in a simple mean field theory. So this is the final photomation predictions. And these look, pretty comparable to old data from ZX Shen's group and also data from Peter Johnson's group, where you even see some signs, very weak signs of something at the back of these pockets. They also have exactly the right volume. More recently, we've started looking at, where's the blue one zone? So one of the things we've been looking at over here, then, there's no Fermi surface, but we can ask, well, what happens away from the Fermi surface? What is the shape of the spectrum? And there's just volumes of data on that, especially by the Stanford group. On the spectrum here, the gap spectrum here, that's the pseudo gap spectrum. So yeah, this is what the data looks like. They get these peaks, but just look at the blue lines. They look like this near the antinodal points, and they look like this in the nodal points. And our computation can reproduce the details of that. It just works out, with no. But there are a few fitting parameters, but the same fitting parameters work, everywhere in the blue one. So there's much more data than there are fitting parameters, and it works very easily. We can also ask, what does the spin liquid do? Well, what the spin liquid will do is scatter, has low energy excitations that can scatter the electrons on the Fermi surface, the wrong size Fermi surface here. That's a higher order effect. And so we're not very sensitive to what precise nature of the spin liquid is. And that gives you, spectral line shapes that have long tails. And again, we can fit that quite reasonably by essentially the same model. Anyway, so I don't think you want to know all those grungy details, but I hope you'll believe me that after many years of trying, we have a theory that fits the experiment much more easily than anything we've tried before, and also has, I think, a very sound theoretical basis. Okay, so I'll conclude there. So I've given you 2 recent experiments which are showing indications of the power of spin liquids. One is seeing the basic spin RBB state in an experiment on Rydberg atoms, where there's some evidence for the deconfined phase of a Z2 gauge theory. You can always write any model as a gauge theory. So just saying you have a quantum simulation of a gauge theory is not saying that much. The question is really, do you have a deconfined phase of it? And if you take that criterion, this is one of the first pieces of experiments like that. And the second is I think, putting new life in old theories of the pseudo gap metal, put them on a firm theoretical basis, where we can rather easily fit whole sets of data. And this gives us at least an intermediate temperature range where we think there is a spin liquid. And the basic trick that's new here is you don't fractionalize the mobile electron. You pick any paper, including mine from the old days. You take the electron and split it into a holon and a spin-on. That's been the dogma of the field. The trouble is that's very hard to do because it's the spin interaction, which of scale J, that wants to form fractionalized things. But the hopping of the electron is much higher in energy, is the scale T. And that is an attractive force between holons and spin-ons. So the electron doesn't want to split into an holon and a spin-on, as people have been saying for 20 years. What you should really think about is the spin excitation of the paramagnons fractionalizing. Once you do that, the theory just falls into place. Thank you.
In the second part of your talk, you mentioned this C operator which measures the coherence between and diameter.
Yes.
So is this operator, can this operator be found in other lattices also, for example, in Paramagnon?
I believe so, but again, that's really a question for Julia. So it's not, you have to come up with the right experimental protocol to measure that object, this one, I guess, which is just verified here. But so you have to do some time-dependent changes in the potential. But I think if it's sufficiently clever, it can. I think Julia will correct me if I'm wrong.
Yeah, no, we find a very nice way to do this. So you need to do a basis rotation to be able to measure this, and we found a nice way to do this by applying a quantity system. I wouldn't say it's trivial to do it in other lattices. You need to find a way to map eigenvalues of Z to eigenvalues of X. So I guess it's possible, but you need to come up with a strategy to do that.
Yeah, I actually had one question each part. The second part is, the question is really, okay, it is on the theory. But the second part, I understand your theory and let's totally accept, since you are involved, that it solves the problem of the what is the volume. But does it give superconductivity? We study high EC because the EC happens only 90 Kelvin. If there is no superconductivity in the theory, how can any of this be? It's almost like a philosophical question.
No,
I don't work in it.
Yeah, of course. Sure, we can write down a theory that's superconducting. In particular, we can write down a theory which gives you a superconductor, which is a confining state. So we at least can have these very simple endpoints where you start with this FL star state, and then you condense the right object, and it gives you a superconductor, which is a conventional BCS superconductor. Really, the question is, can you quantitatively compute this and really understand what's the critical temperature and how you go from one limit to the other? Yeah, no, we're a long way from that. That's a much harder problem.
And as you know, you started with the cover. It's a very old story. It's not even clear it has superconductivity.
I could basically, I want any one band model with strong local correlations. I mean, there's nothing at the level we are working on, which is a lot of free parameters. We can't tell you anything about the Hubbard model per se.
The first part, my question is actually a bit more, how can I put it, a bit more delicate. As you know, I have been working on one topological phase for the last 21 years. That's a free Fabian model.
Yes.
No question about it. If
Yeah.
you do an atomic experiment like that was done, you're going to see free Fabian. It's just free Fabian. There'll be no other results.
Yeah.
People do experiments.
Yeah.
They see things and immediately point out, no, it's not that. Problem is that the theory clearly predicts something.
Yeah.
It's almost impossible to avoid cross production bias, even for a free Fabian model, which is like the world's simplest model. So I worry about that.
Yeah. Well, look, I mean,
19 atom lattice. Okay. You make precise predictions, experiment doesn't quite see that. This is something we should always keep in mind.
No. All right. Fair enough criticism, but I will say that first of all, here there's a microscopic information that you can only dream of in the Majorana system. You can see every atom, you can see every qubit. Of course, it's a destructive measurement, but you can see every one of them. And so you have a lot of microscopic information, and so you can at least see microscopically what are the type of correlations that are building up. And I think there's clear-cut evidence here that these type of RVB correlations are building up. That I think is a reasonable claim that's made in this paper. Does this mean in the thermodynamic limit we're going to get a spin liquid? That's a much more difficult question. For that, we will have to do what Majoranas also have to do, is find two anyons and braid them. That hasn't been done here. But there's the other experiment by Google, which literally is building a toric code. And they claim they have some baby steps in braiding them, and they see correlations consistent with the anion phase factors. But there are no doubts there because they are building the toric code. It's all an experimental on the theory side. So it's purely an experimental question. How important are your dephasing? And
I can do that in a digital computer 20 qubits. They should see it because I see it in digital simulation.
Yeah.
And the concern, I'm not questioning that these correlations are there, but what my concern is, as you increase system size, does something else happen? Like in Majorana, what happens is disorder.
Yeah.
Because those systems have disorder, and then we can show it goes away. So that, this is, I've not looked at it. I'm not saying that's what happened, but it's a big concern is what I'm saying.
Fair enough. I mean, it's just a question of, at least that's okay. I don't know, Julia. I'm really talking about things that Julia will discuss, and really she knows much more about than I. It's the question of what do you want to use this for? So we want to use this for some quantum simulation. maybe do some, I don't know, I think certainly there's a recent experiment also by Misha's group, which Ryan and I have had some passing involvement, trying to do some quantum adiabatic computation, minimize some constraint problems. So you don't need perfect decoherence, you don't need perfect anyons, you're just trying to, yeah. So I think that's another important direction.
Yeah, that's the kind of thing I was.
I can't, maybe you can take off your mask. Yeah, it's all right with me. So if there was a lower layer was a valence bond solid, that would double the unit cell. Then in the double unit cell, a small Fermi surface is a conventional Legendre surface. Okay, once you double the unit cell, it's only mod 2 that matters. So if you had 2 electrons per unit cell, you don't care. Whether you have volume P or 2 plus P, doesn't matter. They both obey the Legendre theorem. So, or 1 P and 1 plus P. When you double the unit cell, they become 2 plus 2P and 2P and per unit cell. And 2 is equal to 2 plus 2P. You know, so you have, see here you have a volume 1 plus P per unit cell. You have volume P per unit cell, NFL star. Suppose I double the unit cell, then this is volume 2 per unit cell. Sorry, 2 times 1 plus P. So, you know, in FL star, you have Fermi surface of volume P. In FL, you have volume 1 plus P. Now you double the unit cell by a valence bond solid. Then here you have volume 2P, and this is 2 plus 1 plus P. And these are equal to each other mod 2. So they're both Legendre volume Fermi surface. Then this is not an interesting situation in the sense of spin liquid physics. Yeah. Yeah, so the whole Legendre theorem very much tied to translational symmetry and whether the translational symmetry is realized in a non-trivial way in the spin liquid sector or just in terms of the Fermi surface. So in the valence bond solid, the translational symmetry is kind of trivial. It's just broken, and you have double the unit cell. But in the when Legendre volatile metal, the translational symmetry is realized in a very non-trivial way on the spin liquid. And the advantage of this formalism is that all the amazing work that Meysam has done on how translational symmetry is realized in the spin liquid, we can just use unchanged because we actually have a spin liquid. Even in the metal, we can just use it because all the spin liquid physics has been put in an insulating layer. That's really another technical advantage of this approach.
Oh no, that would be very bad. Meysam is very proud that what he's doing has nothing to do with reality. Very proud. He tells me almost every day.
What part of this construction depends on the system being at a high enough temperature?
Yeah, I would love to be in a universe where this worked at 0 temperature. It doesn't. You can see from the experiments. But it provides an excellent fit to the experiments, even at these. I mean, these temperatures, you know, 150 Kelvin, are still very low compared to J, which is 2000 Kelvin, or the Fermi energy, which is 10,000 Kelvin. So we're almost, you know, 150 K seems high, but it's not that high. And so really the claim here is that we should really think of this region as the ground, as a quantum state. It's not a thermally fluctuating state or something else. It's a quantum state with its own properties, which in some more friendly universe would be a ground state. In our universe, it seems to become a confining state. And so the challenge is to understand that confinement transition.
I was wondering if you will, I think if we add more layers of the answer, like truncate the rotor to higher.
You could. I mean, you have to have an even number. They're just making life more complicated. Of course, you'd have more and more parameters. You can, if you think in terms of variational wave function, like this one here, this is a variational wave function. Yeah, right there. This is a variational wave function. You get more parameters. You could. It's just. Yeah, well, I mean, it just gives you more degrees of freedom by which to improve your wave function. I mean, the difference from the tensor network and the PEPS approaches is we are actually using fermions here. These are fermionic, so we really do stated determinants, which they have a very hard time doing, although they claim they can someday. But that's the difficulty here. These are fermionic qubits, not bosonic qubits. But as far as the theory is concerned, which is what we've been doing, trying to write down simple mean field theories and also gauge theories for the transitions between the different phases, which I didn't talk about at all. There's many papers on that. This is sufficient. 2 layers is enough, but you could add 4, 6, 8, yeah, if you want to. But you can't add an odd number. That's the key point. And there were some early papers that add in an odd number, which is wrong. Yeah.
There were no other previous work that rationalized some collective mode.
Not for the single band Hubbard model, not that I know of. Yeah, they all, for the doped Hubbard model, every paper takes your C, you know, and there's one huge collection of papers that write C in terms of a spin-on, fermionic spin-on and a bosonic holon, or it writes in terms of a Schwinger boson and a fermionic holon. Everyone starts with this, and then you get some fractionalized degrees of freedom. But then you say, well, you fractionalize all the electrons, but a few of them you're going to bind back together into electrons because I get this small pocket. So I want to fractionalize all the electron, and then fraction P of them I'm going to bind back together. It's perfectly reasonable. I said it too, but nobody knows how to compute anything with that picture. Now we're giving a way to compute it, and the simple way to do it is just don't do this. Always think in terms of the Kondo effect, the fan, and add double layers every time you want, and then it becomes so, it's amazingly right. Okay, I know I keep saying this is simple, but yeah, I could have saved years of my life, in fact.